All right, this lesson I'm going to go through one way of solving differential equations, and by extension, the way of solving initial value problems. This only works on a special class of differential equations called separable differential equations, um, and the technique is called separation of variables. Okay, so go back to what we did before. We have a sort of straightforward, familiar uh, um, differential equation here. Derivative of f of x, or f prime of x, equals 2x squared. So we know that f of x, right, is the integral of f prime of x dx. So we just do the integral, like this, and we say, okay, so f of x equals the antiderivative of 2x squared, which would be 2/3 x cubed, plus c, and we've got our answer. Okay, so this one's really easy. So that was the really easy one. One more thing that makes this really easy is all we have on this side, on the right-hand side of our differential equation, is an x term. Right? We only have x's on that side. We don't have any other variables. This is where it gets a little more complicated when we have to solve one like this, a differential equation where, like this, f prime of x equals negative 2x over y. So this y here kind of throws things off, and we'll have to take a different approach. So this is what I'm going to show you now. First thing to do is think of f prime of x. It's a lot easier to do this if you just write this as dy dx instead of f prime of x equals negative 2x over y. It's called the Leibniz notation. So use the Leibniz notation here. It'll make things easier. Then what we're going to do is separate the variables. So everything having to do with y will go on one side of the equation. Everything having to do with x will go on the other side of the equation. So we'll multiply both sides by dx, and we'll multiply both sides by y, or 1 over y rather. No, sorry. Sorry about that. Actually, I'm going to multiply both sides by y, right? Over here. And so these y's cancel out, these dx's cancel out. And what have I got? Y dy equals negative 2x dx. Okay, well, what can I do with this? Well, seems weird, but you can actually just take the integral, or the antiderivative, of both sides of this equation. So we can say the antiderivative of y dy equals the antiderivative of negative 2x dx. Well, now we know how to do this. Well, the antiderivative of y dy is just going to be 1/2 y squared. And the antiderivative of negative 2x is just negative x squared. And then we have a plus c. Some of you might be thinking, well, why don't I have a plus c on this side and a plus c on this side? Just as a little quick side trip over here. Suppose I'd written it like that, 1/2 y squared plus, I'll call this c1. This constant of integration equals negative x squared plus c2. Well, to make it simpler, I might just subtract c1 from both sides. I get 1/2 y squared equals negative x squared plus c2 minus c1. Oh, well, c2 and c1, I mean, it's not like we know what those numbers are. It's not like they actually have any value. They're just random constants. So we could just say, well, we just combine those into one. Why write two constants when we can just write one? We'll just call that one constant, whatever this is, c2 minus c1. We'll just call that c. And so we end up with the same thing. All right. Leave that, just kind of bracket that for now. That's just in case you were confused. Okay, and then we've got over here, just to finish up, we've got 1/2 y squared equals negative x squared plus c. This is an implicitly defined function right now because we don't have y by itself explicitly stated, but we can get it there if we want. We could say y squared equals negative 2x squared plus, now again, we could call this 2c, right? But it's just some constant, so why don't we just call it c? All right, 2c and c, it's not going to make any difference. And then to get this by itself, we would have to take the square root of both sides, so we get plus or minus square root of negative 2x squared plus c, and that's it. Okay, so that is how to solve a differential equation by separation.